nedense. Ha, şimdi oldu sanırım, evet. Pardon, başa dönmem lazım.
So it is our pleasure, great pleasure to have Berkan Uze from Boğaziçi University. He will give an informal overview of higher geometry, which will be a preparatory talk of tomorrow's seminar of Urs Schreiber. Yeah, thank you, Berkan.
Thank you for introducing me. So the idea of this, I mean, this was a very impromptu lecture. And to be honest, I was thinking about these things maybe like 4 years ago. And now I've been working in the algebraic geometry exclusively for a long time. And while I'll deal with higher categorical objects all the time, I mean, they are the foundations of sort of everything I do. I have not thought about them in the way that Schreiber does in a long time. So it was an interesting experience, sort of catching up with myself from 5 years ago. But anyway, so this is intended to be a kind of refresher of notations, more or less. So I hopefully maybe it will clarify certain things tomorrow. I'm sure Schreiber will also go into some of these things. But I thought maybe like prior exposure wouldn't be bad. At least we can discuss certain things among ourselves before we plunge into Schreiber's lecture. So first of all, what is meant by higher geometry? For us in this context, it means geometry in an infinity topos, and we'll discuss what that is. So for higher geometry can have many different meanings. Higher algebra, things like that, I mean, have huge currency right now in different disciplines. So I mean, there are like higher homotopic algebraic geometry, derived algebraic geometry. All of these things participate in this notion of higher geometry, but the different flavors of that notion. So in this lecture, we confine ourselves to the sort of higher geometry in the sense of Schreiber and collaborators, sort of mathematical physicists who deal with infinity categorical formalizations. I mean, in a very serious way, but their focus is differential geometric and mathematical physics inspired. So, I mean, it is a very particular flavor of higher geometry. And my plan is to basically just state what a principal infinity bundle is supposed to be and then to recover the extremely pleasant and almost tautological classification theorem for moduli infinity stack of infinity bundles. I mean, this by recover, I mean we recover what the usual statement for Ban-G, which is, you know, homotopic classes of maps from X to the classifying space. So we recover exactly that, except in an extremely alien and general context. And this is very pleasant. So I hope to just state this. So the plan is, obviously we need to cover a lot of ground. So what is an infinity category? What is an infinity groupoid? What is an infinity topos? And then having some black box notion of these, we can discuss, again, very briefly, group and groupoid objects. I mean, this is backwards, groupoid and group objects in infinity topoid, or more generally in infinity categories with some like minimal properties. Infinity group actions, and then principal infinity bundles. And this cohomology bit, I'm not really going to do much with that, just to state what a cohomology and infinity topos is. So let's start with what is an infinity category. I mean, I guess anybody, like most people, have heard of this if they're participating in this seminar, but so just as a notational refresher, what I want to do is not to just rediscover infinity categories in this lecture, but to discuss the nerve construction, which gives a very intuitive picture of why simplicial models, why simplicial sets obeying certain conditions model what we want to think of as an infinity category. So let's discuss that. So first of all, a simplicial set, recall that is a sort of is a contravariant functor from this ordinal category, which is also known as the simplex category, which consists of just strings of this form, like ordered, essentially just ordered set, finite ordered sets of this form, with morphisms that are just order preserving functions between these strings. So this is the ordinal category. And the simplicial set is just a D-shaped diagram in set. So it's I mean, we'll see more concrete examples of what this means. This category is supposed to encode the combinatorics of higher dimensional shapes. Higher dimensional simplices are built up inductively from lower dimensional ones. So simplicial sets assemble into a category, which is just this pre-sheaf category. This is the category of simplicial sets. And this category inherits a generating set of morphisms. Can I annotate on this? I was hoping I could write on the slide, because ordinarily I can annotate during a live lecture. Is that possible?
I hope so.
I don't see an option. I mean, normally it shows up at the top when I open a Zoom session, but it doesn't seem to be there. Maybe because you don't have a license. It's your
probably.
meeting.
Yeah, probably. Yeah.
So then that's out. That's a shame. I was hoping to illustrate some of the simplicial stuff, but I guess we'll have to settle for words. Anyway, so that inherits a generating set of morphisms from the simplex category, which I will not state, called face and degeneracy maps, which map the sort of this. I mean, recall that this xn is the sort of the nth level of the D-shaped diagram I mentioned. So this D-shaped diagram is a kind of consists of levels corresponding to integers. So these are like very, very informally, these are the kind of the nth level of these simplicial sets. And the face maps and the degeneracy maps interpolate between different levels, and in a way that, you know, they obey certain relations governing how they interact. Ordinarily, I would have drawn some of this sort of for lower dimensional simplices, but I'm not going to be able to, so I'll skip this. So what is an infinity category? Going on with that idea, I want to define how to build a simplicial set out of a small category, some ordinary category. So let's define NC to be the simplicial set with the simplices, NCN. And NCN is just for each N, NCN is the set of composable N strings of morphisms in C. So these C, C0, C1, these are objects of C. Like any such composable string in C gives an element of NCN. And concretely, the simplicial face maps here acts in the following way. So it sends an composable string like this, sort of a string of n composable morphisms to this string of n-1 composable, so n-1 string of composable morphisms. And what it does is just skip the CI level. So everything else is unchanged, but the DI face map tells us to kill CI and then compose FY plus 1 with FY. And that's all it does. So this is the face map lowers the dimension of the simplex in this way. And the degeneracy map sort of reduplicates CI. So it just inserts an identity map in the middle here, and then the rest is unchanged. So it gives us a map to the higher, sort of one higher dimensional simplex. So this gives rise to NC this gives rise to, now that we have like discussed what the objects are and what the face and degeneracy maps are, this defines a simplicial set for us. And this is called a nerve of a category. Let's see, before we say more about that, let's see what that says about the structure of a category C. So consider NC0, just set of 0 composable morphisms. These are just vertices of the simplicial set. So these are just objects of C, right? I'm 0 composable morphism, that means just objects. So it's the set of objects of the category C. The equally obviously, the set of 1 composable morphisms is just the set of morphisms of C. So that's our first level of the simplicial set. And in this case, the phase map D0, D1 are just source and target maps. This is very easy to see. So this already defines for us like the rough features of a formal definition of a category, right? Source and target maps between ob and more. So we have already the skeleton of a notion of a category. Then the degeneracy maps encode identity morphisms on objects, which, again, further filling up the data of a category. And then we go up, the higher simplices will encode compositions of morphisms, things like, identifying FG as a kind of, as the composition of F and G in a kind of geometric way. So there will be all these higher diagrams, which gives us compositions and then associativity of compositions and homotopies between, and all the higher homotopies that witness all these relations. I mean, this is not an easy idea to immediately convey, but I hope that at least the first couple of levels make it clear that, the nerve construction gives a kind of decomposition, like homotopic decomposition of the notion of a category, and then they are recoverable from each other. I was hoping to draw some of this as well, but so the nerve construction actually defines an embedding from cat to simplicial sets. It is an embedding because every category gives rise to a simplicial set under the nerve construction, but not every simplicial set, crucially, is an infinity category. We'll get to that. But this nerve construction can be composed with the geometric realization of simplicial sets. I mean, this is the same construction as geometric realization of the singular complex, things like that. In the context of elementary algebraic topology, it's the same geometric realization, which creates up to homotopy equivalence a unique topological space out of a singular like the simplicial complex of a topological space, for instance, this is how you create a topological space out of a simplicial complex. And then, so this gives rise to a functor to topological spaces, which is just a famous classifying space construction, it turns out. So, this is a familiar object. Classifying space of a category consists of the topological space, which encodes precisely this sort of kind of categorical data. So it converts category theory into homotopy theory of this topological space. I won't go into this. This is a classical topic, but it needs to be reviewed on its own. So I said that not every simplicial set is an infinity category. I mean, we haven't really discussed what an infinity category is, but if that was true, then I wouldn't say, this would give rise to an equivalence or something. So we say a simplicial set is said to be a weak Kahn complex. If every diagram, again, I was hoping to draw here because it would be easier, but if every diagram giving us this so-called horn inclusion, a horn is like, imagine a diagram, but the ith face is deleted. So like it's for like n equals 3, that's just literally a horn, like a span, in category theory, or just a correspondence, something like this. So you just delete the ith face of your, say, simplex, of your triangle, let's say, and then what results is the so-called ith horn. So what this says is like, for every such inclusion of every such shape in our simplicial set, so-called outer horns, very importantly, I is not like the zeroth horn is not included in this condition. There exists a dotted arrow making the diagram commute. In other words, there's a way to complete all horn inclusions, like all horns inside X, uniquely up to homotopy. This is again a geometrically, if drawn, this would make sense. It roughly says that all these kind of tautological diagrams witnessing things like composition and associative composition of morphisms are going to be automatically commutative in the appropriate sense. They can be completed up to infinite, like Tower of Infinite homotopies. But I mean, imagine like the n equals 2 case is illustrative, I think, where, you know, you imagine a horn-shaped diagram in X, and for that horn to be fillable, it means that, you know, let's say you have F and G, and say you have like 2 morphisms, F and G, from some, like between some objects, and for that horn to be fillable literally means you can compose F and G, okay? And then imposing this condition for arbitrary n tells you like that composition makes homotopic sense. But again, this is like a very hard idea to motivate if you're not already used to thinking about this. But it's useful to think about the second dimensional case where, you know, the horn fillability is just, it makes sense to compose morphisms in a kind of appropriately unique sense. And for this reason, we say a simplicial set that is a weak Kahn complex is an infinity category. Something that obeys this Kahn lifting condition is our definition of an infinity category. And it is a foundational theorem of infinity category theory that nerves are precisely weak Kahn complexes. So the simplicial sets that come from categories under the nerve construction obey this condition already. So, I mean, this can be taken as a kind of foundational intuition of why we define an infinity category as a weak Kahn complex. And a category can be identified with its nerve as well. But we say abstractly, a general infinity category is a weak Kahn complex. So, I mean, this is a kind of notational point. And obviously, having defined infinity categories, it's desirable to define infinity groupoids. Infinity groupoids are the sets of the higher categorical world. So they form the kind of natural enriching base of infinity categories, in the sense that the home spaces of an infinity category naturally are naturally infinity groupoids. But what is an infinity groupoid? Infinity groupoid is a simplicial set for which I can equal 0 here. So all the horns, not just outer horns, can be filled. So we call these simplicial sets Kahn complexes, if all such horn inclusions can be completed to a commutative diagram in this way. And the condition that all horns can be filled, including this lambda n0, like the 0th horn, transcribes the invertibility of all morphisms. Again, if you just draw what these horns are, this is very easy to see. So including this I0 allows us to define an inverse of every morphism. So literally we can just, I mean, this condition gives us an inverse for every morphism, guarantees the existence of an inverse for every morphism. So it turns out the Kahn complex is an infinity categorical analog of a groupoid. I mean, here by a morphism, again, like this is a simplicial set. We have infinite amount of data, but the morphisms are the edges of our simplicial set, right? I mean, I don't know, like imagine how are you thinking about a simplicial set? You have points, just as in here. Then you have strings like this, and you have like higher shaped diagrams like triangles, tetrahedra, things like that. So the vertices are always objects. You can think of them as objects of an infinity category. I mean, it's not such a well-defined notion, but we can think of them as that. And the edges of these simplices are morphisms. We refer to them as morphisms. And then we have higher shapes giving us more diagrams. But so in the sense, every morphism in an infinity category is invertible. So it is in a Kahn complex, sorry, in an infinity groupoid is invertible. So that's why we refer to them as infinity groupoids. They are higher analogs of groupoids.
I'm sorry, I'm not sure if this is something you already said, but can we see, or how do we see invertibility in the diagram?
Yes, I was hoping to draw all this, but since this session, this particular Zoom session does not allow me to annotate, I won't be able to. But I mean, if you just, all you need to do is to understand what a horn looks like. And then if you write a zeroth horn, you'll see why this count condition immediately tells us an inverse must exist. I mean, I'm not saying it gives us the inverse or something. I mean, because this would be a very unfortunate phrasing in an infinite groupoid context, but it tells us such a thing must exist in the appropriate sense because this condition guarantees that. But I mean, it's very easy to see when you've drawn them. And
is
then
it in the previous diagram that you...
No. This is not, again, like I was hoping to draw some of this like lower dimensional simplices, but I can't annotate on this session. So I can recommend some sources. And we have this, I mean, as a more formal grounding of this idea, we have the theorem of Quillen, which tells us singular complex and geometric realization functors are mutually inverse and give rise to equivalence between these model categories. And if you don't know what a model category is or what the Quillen model structures are, what's important for us is we have an equivalence of infinity categories between topological spaces and count complexes, which induces a more familiar equivalence of homotopy categories, which is, you know, the homotopy category of topological spaces is equivalent to the homotopy category of count complexes. This allows us to define the category of spaces in the infinity category world as just the infinity category of infinity groupoids. That's why we tend to refer to infinity groupoids as just spaces. And spaces up to homotopy is what is meant, but that's always what is meant in infinity categories. So these are, I mean, these homotopy categories are more familiar, I think. But this is the kind of, this model categorical equivalence is the one categorical incarnation of the infinity categorical equivalence between topological spaces and count complexes. And I mean, the singular complex, if you just think of the usual, like in the usual topological sense of the word, singular complex gives rise to a simplicial complex, right, from a topological space. And geometric realization gives us back a topological space. And Quillen's theorem tells us this is in fact an adjunction giving rise to an equivalence. In particular, every simplicial set that comes from a topological space is a count complex. But this is what the statement says. And so it's we think of spaces, of topological spaces, infinity groupoids, and vice versa. And in fact, one sort of more intuitive model for higher categories would be something like topological categories, where we have the home spaces are topological spaces, and then it's easy to model things like higher morphisms. You know, morphisms are just paths between objects, and higher morphisms are homotopies between paths and homotopies between homotopies and things like that. So, I mean, this topological categories can also, under appropriate modifications, can also model infinity categories. But simplicial set model is more sort of combinatorial and computationally accessible, but it is possible. There are many foundations of infinity categories. I won't go into that, but keep this theorem in mind. So, I mean, what is an infinity topos? First of all, what is a topos? A topoi arose as categorical avatars of topological spaces. So as kind of like the axiomatizations of some very pleasant geometric properties of pre-sheaf and sheaf categories of the form, sort of this pre-sheaves on X. X is a topological space here in this paragraph. So topoi, I mean, the Grothendieck topoi are topoi of this form. They are pre-sheaf topoi on some topological space or on some category. But there is a kind of elementary, there's a notion of an elementary or Laver topos, which gives a completely logic, like axiomatic presentation of a topos. I mean, we are not interested in this. Although Schreiber is interested in this in the higher setting, I don't think there's a written up exposition of an elementary infinity topos that's uniformly accepted. So I don't want to talk about that. But more generally, sort of the paradigmatic examples of topoi are categories like presheaves on some small category C. I mean, C is a site. Let's say it's equipped with what's called the Grothendieck topology. And sort of categories of this form are the first examples of topoi. And in fact, every Grothendieck topos is essentially equivalent to topos of this form. There is a kind of axiomatic presentation by Giraud of a topos as well. But we have a theorem that says like every category that obeys those axioms is equivalent to, like there is such a site such that it is equivalent to a presheaf topos. So, I mean, for us, intuitively, topos is something like a presheaf category or a sheaf category. Not just on topological spaces, but also on, on categories equipped with topologies. So infinity topos immediately generalizes this idea. And a presheaf, what is a presheaf category is a kind of like, I should have mentioned the presheaves of sets, sheaves of sets, I mean, not sheaves of like abelian objects or module, things like that, which are very different. That's a different world that gives rise to what's called an abelian category, which is as different from a topos as it can be. Abelian categories are never topoi. Topoi are never abelian categories. So this is kind of very important, like juxtaposition. The analog of sets in the infinity world are infinity groupoids. So taking like, instead of sheaves of sets here, we consider sheaves of infinity groupoids. So sheaves like sheaves of spaces on a topological space, we should immediately get like the first example of an infinity topos. In fact, anything we define as an infinity topos should include something like that. And indeed, I mean, also more generally, things like presheaves of infinity groupoids on other infinity categories should also be infinity topoi. So as a kind of straightforward generalization. And in fact, I mean, after a lot of work by Resk, Lurie, and others, it turns out there's a kind of, I mean, there's a way to, anyway, let me state this theorem of Resk. An infinity category, I adopt this theorem as a definition of an infinity topos for this lecture. So infinity category is an infinity topos if it arises as the accessible left exact localization of a presheaf infinity category. This is not, the accessible part is not important for us. The left exact localization, I don't know if you're familiar with this category theoretical construction, but if you're not, think of it as a kind of like, think of sheafification, for instance. So this example, this definition is supposed to include things like sheaf categories in our definition of infinity topoi. So we are now considering, like, we fix some Grothendieck topology on this infinity category, which is just the Grothendieck topology on its homotopy category. And then we are looking at presheaves, which says like presheaves of spaces which satisfy some descent property. And then, I mean, this left exact localization in this context is just sheafification, which exists in the infinity world. So infinity topoi are things like, I mean, this definition works backwards, it's like reverse engineers this idea that, infinity topos is supposed to be like a presheaf category, presheaves of, where we're taking presheaves of infinity groupoids, or a sheaf category. So, and this is how we should think of them in this lecture. And I mean, not every infinity topos is obtained as a sheaf category, mind you, but it's easy to think of it in this way right now. I'll skip this because I was hoping to write something down here as well. So maybe I shouldn't dwell on this stuff, on this category objects in infinity categories, because we don't really have an intuition for infinity categories in the first place. So an infinity category object in an infinity category is a kind of simplicial object in an infinity category. So that means, recall that a simplicial set was like a functor from D op to set, simplicial object in the general category is a functor from diop to our like infinity category, where we now consider diop as a like we confuse normal ordinary categories with their nerves. So the simplicial object is as a functor from the nerve of the ordinal category to our infinity category. And so essentially a simplicial object has like we have like these levels again, like before, but these we are working on the infinity categorical setting. So we say infinity category is a simplicial object obeying the so-called Segal condition. And a Segal condition is something that appears early on, actually, very early in the 70s, I think, in the alternative definitions of infinity categories as Segal spaces. And with some work, one can see that like the fact that this map gives an equivalence. I mean, the map here comes from the obvious map, from the sort of, because this is a simplicial set, we have all these maps, right? So this is a kind of canonical map that we have from the data. It's not hard to see that, in fact, this condition is implicit in our lifting condition, in our discussion of the nerve of a category. I mean, it's not immediate to transcribe that, but it can be. This roughly says that like there is a way to compose n morphisms. It is roughly what it translates. And a groupoid object is a particular example of a category object in a topos, in a category. Now we specialize to infinity topoi, and implicitly there are many reasons for this. And infinity topos is extremely well behaved infinity category, but I won't go into like the axiomatic characterization of an infinity topos. So, but we specialize to that context because we want to do higher geometry. And it's a particularly good context for that. And again, like a groupoid object is a particular kind of category object. So it's a simplicial object whose Segal maps are equivalences. In fact, it turns out there's a way to better transcribe this, unpack this, and Lurie's book, Higher Topos Theory, has a very long, very thorough treatment of different ways of encoding groupoid objects, but it is quite complicated. So what I write here may not be immediately intelligible. It's a bit confusing, but the GKs here are like, this is the simplicial. What I mean is the set which corresponds to this ordered, like K stands for the string from 0 to K, right? So that's the subset of N, as a subset of N. It denotes, like for every partition of N into subsets, this gives rise to like these sets which come from applying the simplicial set, which is a functor, to those linearly ordered subsets of N. I mean, this condition looks very complicated, but what I'm writing here is the same thing as what I'm writing here. So this tells us, I mean, the groupoidal business adds an extra, again, an extra invertibility condition. But a groupoid object is like a simplicial, like an internal category object in an infinity topos. So it obeys a kind of internalized version of what should be seen as like this Kahn lifting condition. So if you were to transcribe everything inside an infinity category, like then try to understand what an infinity category inside an infinity category is supposed to be, you would have to kind of deal with these diagrams. Then you would find that like the Segal condition exactly gives rise to something like a weak Kahn condition that we discussed. But it is, of course, the involved diagrams get very complicated. But maybe this category object description is a lot more accessible. A check nerve, let's say let's say we have a morphism in an infinity topos. And then we have the so-called check nerve of this morphism, which is the groupoid object. I mean, don't worry too much about this groupoid object business. Think of it as, I mean, there's an obvious way to form such a simplicial object, right? Just taking the fiber products over Y associated with this F. This is just the usual fiber product of a morphism. And it gives rise to like a simplicial, like this infinite tower of fiber products. And this just like in like the discussion of check covers, check cohomology, things like that. So this is a familiar object. It gives rise to a simplicial object in our topos. And we say, I mean, this is not the most important thing, but we say a morphism is an effective epimorphism. And more intuitively, we say it's a covering map if it is the colimit of its own Chechner. By the colimit, I mean, you take the colimit of this simplicial object considered as a diagram. And then F is an effective epimorphism if it is equivalent to that, considered as a map when you have this obvious map from X to Y. So considered as a map, if F is equal to its own, the colimit of its check nerve, then we say it's an effective epimorphism. If you're familiar with this notion in the one categories, we have, I mean, not every category is as well behaved as set. So we have these bizarre distinctions that seem counterintuitive, like epimorphisms, like effective epimorphisms, irregular epimorphisms, things like that. Things that we cannot distinguish in set have to be distinguished in arbitrary categories. So in an infinity category context, we say a morphism is an effective epimorphism or a covering map if in an informal, like very informally, if Y can be built up from just imposing some equivalence relations on X and then quotienting X by them. So, I mean, this tells us like all of Y can be created out of X with equivalence relations. And there's a way to formally state this, but I think this is intuitive. So, I mean, it tells us Y comes from X in a very particular way from this morphism. So it's an intuitive notion of a covering map, basically. And this check nerve is, I mean, it's literally, this effective epimorphism is literally a like infinity categorical transcription of this. Just tells us to go higher, right? Because an equivalence relation comes like comes from these fiber products. So we have an infinite tower of these here. So what this tells us, like here, it says like, this is a statement about kernels, kernel pairs. But here we have like this higher diagram. And then, so this condition is the same condition as this in an infinity categorical context. And I mean, I'm going to refer to this notion. That's why I wanted to define it. And I think it's intuitive. So now we get to the real point. It's group objects in an infinity topos. So these are particularly defined formally as particular classes of groupoid objects. Okay. So let's retreat back to a more tangible stage in categorification. What's a two group? Well, two group is just, symmetric is not supposed to be here. I forgot to delete that. Of course, a two group is not a symmetric monoidal groupoid. So just a monoidal groupoid with inverses, not symmetric. So we have a product on this category. It's a groupoid, so every morphism has inverses. And then these monoidal operations also have inverses. So every object is monoidal invertible. So that's our definition of a two group, right? I think this is a lot more familiar to the audience than maybe higher categories. A strict two group is a group object in categories. And in the spirit of internalization, this is the same thing as a category object in group. We don't deal with strict objects here, but this is a good intuition. This is what we want to transcribe, a group object in a category. And it's in fact what we do. So we define an infinity group as an E1 algebra in our infinity topos H, such that this sheaf of connected components, pi 0 G, is an actual group in the truncation of our infinity topos. So what does any of that mean? A truncation of an infinity topos is what you get when you kill all the higher data. So what you get is just a category, ordinary category. You kill everything about the higher morphisms and homotopies, So that this zero truncation is just an ordinary category. And the connected components is this is a set ordinarily. Connected components of a topological space give rise to a set, right? It's like a pointed set, not a group. But we say an infinity group with this, some object in an infinity topos is an infinity group if it is like infinite homotopy associative algebra such that its connected components forms a group object. So let me get more intuitive with this. It's impossible to unpack explicitly all the data that goes into the defining a homotopy associative object, but somehow it must intuitively encode like the notion of a group object. So E1 means A infinity. I say E1, but most people I think say A infinity. So that's a homotopy associative structure. And what this means is like, at least we need to have something like a multiplication morphism. We need an inverse map G to G, and we need a unit morphism. So this pointing morphism. But things like the property of the unit, inverses, like relations of inverses, associative multiplication, these things cannot be just encoded by like equalities. We say like the multiplication, like inverse is just some kind of equation. So they have to be actually witnessed by diagrams and higher diagrams witnessing them and things like that. So it's very, it's not easy to see this as a kind of explicit structure, but there's a clever way to package this due to Lurie. I will actually skip this because time is not, I don't have a lot of time, but there's a way to encode all this structure as a sort of infinity group. Turns out to be just an infinity groupoid object where the initial, like just G0, zero level is contractible. And so we have a diagram of the form. So infinity group turns out to be a sort of simplicial object like this. And this is a lot more intuitive to deal with than what's going on here. But the equivalence between these is a theorem of Lurie, which I will not go into. This gives rise to kind of an infinity category of infinity group objects. We denote this by group H. And to state the looping injunction, we have the following notation. So this H point on this denotes the under category of the terminal object, meaning these pointed set, like pointed objects. All these maps from the point to, oh, sorry, that's terrible, like mistake. I don't mean point to H, I mean some X such that there's a like point to X. So these are all like objects X with a map from the point, from the terminal object, not point to H. I guess this also gives rise to a map from point to H, but anyway. And this H greater or equal than 1 denotes the subcategory of connected objects. So these are objects whose homotopy groups all vanish except pi 0. Again, if you think of higher categories as somehow related to topological spaces, this is more intuitive. So it literally corresponds to connected objects. We defined a loop space object functor as this fiber product, as this kind of self-intersection of the point over X. And this seems like a bizarre definition if you have not seen it in different contexts, but it makes perfect intuitive sense. A loop is like a map from the point to itself. And there's a kind of derived intersection going on, of course, but it is supposed to be like a fiber product is like a homotopy kernel. It's a kind of, I think more formally, the loop space is the homotopy fiber of this point inclusion. We could say that as well. So however you want to think of this, formal loop space object of some pointed object is defined by this diagram. And given some connected pointed object X, we can consider the Chechnerv of the canonical pointing map. And I mean, looking at this diagram, if you recall the Chechnerv construction, the first stage was the fiber product. Like the first stage is precisely this fiber product. Let's see where that was. Here. So the X are points here and Y is X. So this stage of the Chechnerv of the point inclusion is just the loop space. And then it goes on further. We have further loopings. And then this looping fiber sequence, which is just a definition of the loop space, gives us this sort of homotopy exact sequence, which is a homotopy fiber sequence. And if G is an infinity group, we also have like the kind of reverse of this, so-called delooping fiber sequence. And I'll actually show you what delooping is in the next slide.
Here, do you mean in forming the sequence, we're applying in some sense, something like an operator, omega, recursively. So we consider loops and then loops of loops and loops.
Well, you would have higher loop spaces. If you look at just the definition of the Chechnerv, you would get things like higher loop spaces. So, I mean, if you continue this inclusion, so what you're taking is the sort of fiber products of the point over X and iterated fiber products of that, you get things like higher loop spaces here. But we are in, I mean, all that data is already packaged here. And we are interested in higher deloopings and things like that. But for like this, all of that data is already in this fiber sequence. And this is just tautological. It's what a loop space is. And the BG I have not defined. It's a very important object. The notation is supposed to remind you of the classifying space of a topological group. And it's also supposed to remind you of when you consider G as a one-object groupoid, I mean, this BG denotes that as well in ordinary category theory. So you remember that every group can be seen as a one-object groupoid, where you have a point and then the morphisms are given by the group elements. And that structure is denoted by BG in category theory. But BG also denotes the classifying space of a topological group. And in fact, this formalism unites them. I mean, so BG in some sense denotes both, but in the infinity category, in the infinity groupoid sense. And I wanted to add a slide on this, but I couldn't. There was no time. But we can discuss this at greater length if you wish. And I mentioned that there's a kind of Chechnerv of this pointing morphism, but this is not important. What's important is this the looping adjunction. So we have this adjunction between omega and the classifying space. And for our purposes, we can define B. I think I'll show in the next slide. B is something that kills the loop space. So B is called a delooping. I mean, originally B is defined in this setting just as the inverse of omega. So, but we already know what B is from other contexts. But in the setting of this adjunction, it is just the inverse of omega. So it is something that when applied to a loop space gives rise to the original space, etc. But it turns out this is actually an equivalence of infinity categories. Group objects in an infinity topos, mind you, it's important that H is an infinity topos in this theorem. It's not true in general infinity categories. But group objects in an infinity topos are precisely connected pointed objects. And this is extremely interesting. And it gives a way to encode an infinity group object in a very, very simple way. Because every pointed connected object gives rise to an infinity group under this adjunction. And then if we have an infinity group, we can deloop that to get an original like pointed connected set. And putting all this together, I mean, intuitively, if we had introduced loop spaces earlier, we could have defined an infinity group as an object of the form loop X for some X. So an infinity group can be more succinctly defined as, like in an infinity topos context, as something like a loop space. And this is historically very authentic, because theory of infinity groups is a generalization of things like H spaces, which are like magma objects in spaces. They are spaces just equipped with a multiplication map and a unit map, so unital magmas, whatever, but no other structure, no associativity or commutativity. And then loop spaces in the original sense of like Peter May and people like that, Boardman, etc. So in algebraic topology. So, and other objects with homotopified algebraic structures like A infinity spaces, A infinity algebras, where you have all these higher data which give you way to talk about associativity in a homotopified weakened context. So infinity groups are precisely sort of abstract analogs of things like loop spaces and H spaces. So this fulfills the intuition. But we are talking about, like, we have just something like an infinity topos, just completely general object. So we're talking about, like, it's very remarkable that we recovered this classical reconstruction idea of a loop space just from this formal structure. And I mean, that what I'm talking about is precisely given by this looping to looping idea. But there's like a loop space recognition there, I mean, algebraic topology, which is precise analog of this. So infinity group actions. So we have infinity, now that we have infinity groups, we can talk about their actions on objects. A G action is a groupoid object. Like this is a G action on P, I should have said. A G action on P is a groupoid object in H of this form. So it is a simplicial diagram given by these kind of, like, these maps encode action of G on P, but we have all these higher data, as I said, because we need to interpolate how this action works, how to define inverses, things like that. So normally for, like, just, you would have, like, in the normal definition of a group action, you would have to, you would truncate here, right? We just have P times G to P. But in the sort of higher categorical setting, you'll have like infinite amount, like tower of data encoding the associativity of this action, that it defines a group action. All of this data needs to be kind of filled in this way. But I think it's more intuitive to see that why this defines an analog of a group action. I said caveat because there's a diagram missing here. Not only is it a groupoid object, but it is supposed to be compatible with G's own structure. So with the infinity group structure of G. So I should draw like the diagram here under this and say that we have like a morphism between this sort of tautological, like trivial G action and this G action. So it is supposed to be compatible with the action of G on itself. But I skipped that here. And we denote the co-limit of this groupoid object, of this simplicial object, by this quotient notation. And we say that this is the infinity quotient of P by G. And this notation is in harmony with the usual notions in algebraic topology, because using all this notation, it turns out we have that BG is equivalent to the homotopy quotient of the point by G in this sense. And this is very interesting because this is exactly what we have in like the definition of a topological classifying space of a group. That is, it is the homotopy quotient of some contractible space, e.g., by the action of G, when it's not free action. But here, mind you, I'm not talking about anything like free actions or anything like that. I don't need to talk about anything like that. And everything's a homotopy quotient as it is. So this is a very clean statement of something we would like to be true. So what is the principal infinity bundle? As usual, let G be an infinity group as we defined. The principal infinity G bundle I mean, G principal infinity bundle, however you want to put this thing, over some object X is a morphism. So it's an object over X, and a G action on P, such that this projection morphism precisely the quotient map. So this morphism realizes the quotient map, like X as the quotient map. Is that definition clear? I mean, if not, think about how this relates to the ordinary definition of a principal G bundle. We have some G action on P, and we have this kind of local trivialization and things like that. But we also have this sort of, we have a transitive free action of G on the fibers of this projection map, etc. And then, I mean, this realizes X as a quotient of P by G in the original definition of principal, like ordinary principal G bundles. And this transcribes all of that into homotopy theoretic language, except, I mean, I have no conditions on freeness. I have no conditions on local trivialization. None of this needs to be stated. Schreiber proves that having given us this, every such data already gives us local trivialization. Like every principal infinity bundle is locally trivial in the appropriate sense of the word, etc. So like we don't have to specify anything further here. And we can just define a principal G bundle as a G action. And it's obvious that every map from X to BG gives rise to a principal infinity bundle. Why is this obvious? I think I stated it maybe I didn't. Maybe in the last slide. Let me get there. So as an intermediate step, like cohomology and infinity topos, infinity topos theory offers us an extremely convenient environment for what you could call very clumsily and generalized non-abelian cohomology, or generally just generalized cohomology. I mean, this kind of continues the idea of Simpson and Grothendieck and others, that sort of there's stacks. You can form like a stack coefficient cohomology, not just like sheaf cohomology with coefficients in abelian groups, or maybe like one cohomology with a non-abelian group, something like that. But you can like consider general stacks, and not only general stacks, but higher stacks as coefficient objects for cohomology theories. And this definition formalizes that idea. We define the zeroth cohomology as the connected components of this Hom groupoid between these two objects. And mind you, X, Y are just general objects in a topos. So we don't distinguish necessarily. We say this is the cohomology of X with coefficients in Y, but we don't have any condition on Y. I mean, in this definition, Y does not need to be a group object. What if it turns out that it has deloopings, so that it is a kind of like, it has a group structure as an infinity group structure? If there is some Z such that BNY, mind you, this can be taken as the definition of BN. So Z is the delooping, nth delooping of Y means Y is the nth loop space of Z, okay? So you can take this as the definition of BN if BN confuses you. So we have this iterated loop space operation. Then we can define higher cohomology with coefficients in this Z, which is now like has some other structure. It's not clear that given an object there exists n deloopings or any deloopings. So that's the same thing as saying like, can you recognize it's an infinity group object or not? Where our theorem gives us a way to see like every pointed object, connected pointed object is an infinity group. So it's an infinity loop space. But I mean, a priori it's not clear. But if it is given, such a delooping is given, we can define higher cohomology as this cohomology. So as the connected components of the Hom groupoid between X and the nth delooping of Y. And this gives us a very, very general notion of cohomology. And so because of this definition, we refer to maps from, say, X to, if like X to BY, X to Y, or X to BNY as cocycles. infinity co-cycles because they give us elements of cohomology infinity group, like cohomology. These are groups because these are like, well, this is not a priori a group. These are just pointed sets. But if there's a group structure on this object, then these become cohomology groups, etc. So we get to the statement of the classification of principal G bundles. Principal G bundles are classified by these infinity co-cycles, maps from X to BG. X is a general element here, and G is an infinity group, and BG is its one looping. So a principal G bundle over some element of our infinity topos has this sort of classifying infinity stack, BAN GX. I use the same notation as the usual notation for moduli space of principal G bundles. And it turns out this BAN GX is equivalent to this Hom groupoid of maps from X to BG. And this is an incredible statement, but it hides some things that I haven't mentioned. First of all, it needs to be proven that BAN GX is actually an infinity groupoid and not just an infinity category. I mean, BAN GX is a very complicated category. Think about how we define principal infinity bundles. So somehow we package all of this into an infinity category, and then I claim this is an infinity groupoid. And this is actually not hard to prove, but it's not self-evident. And so this classification theorem is precisely what we would expect, because in the normal setting, principal G bundles over some topological space are precisely given, like classified by homotopy classes of maps from X to the classifying space of G. I mean, this can be taken as a definition of the classifying space of a topological group, right? A classifying space is precisely like a way to form a universal bundle for some group G. And you can add further structure here. You can add connection, etc. I haven't discussed that, but there's a way to encode things like connections and then add further data. This classification theorem is almost a tautology. Given this setup and given this definition, I can't immediately state why that is, but it's almost a tautology. And more maybe to try to explain why that might be. So this equivalence maps a G bundle PX to a morphism X to BG, to morphisms which can give rise to fiber sequences of this form. So fiber sequence is a homotopy fiber. It's an exact sequence in homotopy sense, right? So this is the kind of you have a point inclusion A to X, and you have a map, and P is the fiber product of that. I was hoping to draw some of this again, but it's here. So this truncated diagram puts all the data together. So I say truncated because we have the data defining a principal infinity bundle can be continued. Like if you take the check nerve of this principal G bundle map, then you get an infinite tower here, right? And that's just the data defining the G action. And this point inclusion is in fact just comes from the definition of BG here. So if we continue all this, I mean, it turns out that BG serves the same role in this setting as it does in the classical setting, is that it is the kind of universal. This point inclusion is in some sense the universal principal G bundle for some given infinity group, in that every principal bundle P over X can be realized as a kind of homotopy pullback. So this is what this statement says. This equivalence says in some sense, every principal G bundle can be obtained as a homotopy pullback of this universal G bundle. And but this is not. I mean, this is not easy to. This is not a proof, but I think particular examples of principal G bundles which arise like this turns out to include all principal G bundles. That's what the statement says. But it's not explicit, of course. I mean, and also it's not clear that because we're considering infinity, like G infinity groups and things like that, it might not be immediately clear what this has to do with like principal G bundles in the first place and things like that. But I'm not going to, I mean, I don't have time to go into examples. I don't think there are many examples of infinity groups in the first place. So what you would consider like is truncated groups like B string or something like that, which are like 2 groups and 3 groups. And examples of infinity groups are not so abundant. But so I mean, the kind of notational introduction.
But there are examples known, right?
Yeah, of course. I mean, it's just if you fix some infinity topos that's familiar, if you work in like, say, infinity topos is just infinity groupoids, which is like the point infinity topos, so to speak. It's the infinity category of sheaves on the point infinity groupoids. And that's an infinity topos, of course. And that is H1, like, sorry, group object there is just the usual AA infinity spaces. So these are spaces that are equipped with a sort of homotopy associative multiplication. But that's what I call E1, and A infinity is the usual name, I think. So if you take the H as the infinity groupoid topos, then every A infinity space is an example. But every infinity space is like a loop space. So every loop space is an infinity group in spaces. Okay. So of course there are like millions of examples. But if you're working on a general infinity topos, then what does example even mean? So if you're working on things like sheaves of infinity groupoids on manifolds or something, and these are kind of topos theoretic analogs of like this allows you to do higher geometry in the differential geometric context. And then like group objects and such things, I don't know what they look like, but they are stacks with group structure. Everywhere I say like element of an infinity topos, you should hear the word in higher stack. And if somebody is talking about higher stacks or infinity stacks in this context, they mean just an element of an infinity topos. But in this context, I mean, that word means a lot of things. They are not all the same, and they are related. But for us, a higher stack is just an element of an infinity topos. So that's just the space with some structure, right? It's an infinity groupoid with some extra structure. And so, yes, generally an infinity group is an infinity stack that has some kind of group structure that is like a loop space structure. And this is very bizarre if you think about the object level. But if you think about the formalism, it immediately it just recovers everything we know about principal G bundles, G actions, infinity groups. So, and Schreiber's great intuition, I think, as far as I understand it, was like the setting of an infinity topos was precisely the setting which allowed these statements to be true, unchanged. I mean, it's a remarkable thing, but this is why infinity topoi were adopted as the formalism for higher geometry, because statements like this had immediate geometric content, and they were almost automatic. Like it didn't take infinite amount of work. Once the foundations of infinity category were set up, which is infinite amount of work, literally, but once they were ready, then these statements made sense in a general infinity topos, not just in spaces and not just in like, I don't know, like just pre-sheaf categories. Like algebraic spaces. I mean, if you are familiar with these kinds of generalized spaces, it makes sense to go all the way. And it turns out like this makes sense, and this statement can be almost immediately seen to be true once the definitions are properly adjusted homotopically. And I think tomorrow, because this work has advanced considerably, and so I'm eager to hear about this sort of equivariant geometry. It builds on this idea, much older idea, maybe a decade old, of higher infinity bundles. So I wanted to give a refresher on that as an introduction.
So Berkan, thank you very much. So tomorrow we have the seminar of Urs Schreiber. I think it's at 2:30, but I'm not so sure whether it's 2 or 2:30. So you should check. Semih, maybe you already know. I guess it's 2:30. So, but anyway, you all should check. And also, Berkan, please fill up the details of your slides with your own computer and then send to us so that we can post it in the web.
Oh,
okay?
Yes. I'll add some annotations.
And some diagrams maybe, right?
Yes.
Yeah, excellent.
So, did you have any questions, by the way?
Yeah.
Well, can we put the slides? Can you share the slides so that they are maybe available?
I'll add the annotations this week, and I'll send you. Send you that file. I mean, I'll just type them. It may be easier.
Okay.
Any questions about the content?
Well, it's an excellent talk. We have, I got some idea. Thank you very much, I mean.
Thank you.
Thank you.